talk about homeostasis. Homeostasis just means balance. So we're talking about the balance of chemicals in your body primarily. All right. An individual cannot live unless they can stay warm, find water, and find food. The body maintains an elaborate monitoring system to ensure that the individual is aware of thirst, warmth, and hunger. It is so important to the body that the body maintains several means of monitoring for each system, and this is known as redundancy, the need to have more than one way of seeing things or determining things. The nervous system coordinates these regulatory systems. The brain closely monitors temperature, water supply, and nutrient supply by using a variety of neural and hormonal mechanisms to keep them within the critical range. If we have excess of any of the three, our bodies have ways of shedding the excess to maintain our level of homeostasis. This is usually done without our knowledge. Seeking either shelter, food, or water is to seek a primary need. This type of behavior is known as motivated behavior. The systems used to regulate temperature, body fluids, and metabolism are negative feedback systems, kind of like your when you're pumping gas into your car. It's a negative feedback system, so your car needs gas, and you keep pushing on the lever, and as soon as the tank is filled up, then it tells the nozzle of the hose that it's full, and it kicks off, and that's exactly the way that all negative feedback systems work. It tells you that you need it, and it just keeps pumping it out until there's an indication that you have enough, and then it turns off. When an individual goes beyond a set point to the level for one of the primary needs, the brain is informed of the negative level like a warning light on a gas gauge. Because we are constantly burning fuel, utilizing and breathing out liquid, and entering into different environments, the process of maintaining homeostasis is a constant balancing act. Losses that we must have, that we cannot get around, are known as obligatory losses, and they obviously require constant monitoring of primary need levels. Cooling not only slows the action of molecules, but it slows the chemical reactions in cells as well. Enzyme systems in most mammals and birds are most efficient at normal temperature, 98.6 degrees Fahrenheit, about that for humans. Actually, my temperature runs in the 96 range, but that's neither here nor there. I guess I'm kind of cold-hearted. Any higher temperature in the protein molecules do not bind properly and thus cannot function as they should. And this is one of the reasons why you have fevers. If you have a fever, then your body stops being able to process chemicals as readily as it was before, and whatever bacteria or virus that is causing the problem will die. Viruses are very fastidious. Bacteria, not so much, but bacteria also, if you starve it, then the bacteria will die. The virus, if you heat it too hot or you cool it down too much, it'll die. So that's one of the reasons why your body functions the way that it does. If you are sick, then you will start running a fever, and the fever is there in order to kill off either the bacteria or the virus. At very high temperatures, the amino acids in the proteins break apart and begin to fuse together at random. The protein in the brain is especially susceptible to high temperatures, and this is one of the reasons why, if a child has a high temperature, then the doctors are very adamant about bringing down the child's temperature, because if they don't, there could be brain damage. Prolonged high fever can cause brain centers that regulate heart rate to die, thus killing the patient. At very low temperatures, the cellular membranes are disrupted by the formation of ice molecules, and even when thawed, they cannot reform properly. Warm-blooded animals generate heat from the inside to keep themselves warm and thus are referred to as endotherms. Endotherms generate heat by burning food in the body, a process known as metabolism. Heat inside the body is measured in kilocalories. 1 kilocalorie is enough heat to raise the temperature of 1 liter of water 1 degree centigrade. An adult can burn as many as 600 kilocalories per hour with strenuous exercise, but only 60 kilocalories when they're resting. What was I? Oh, we used to have horses when we were in Montana. And it gets very, very, very cold up in Montana. Sometimes uh, below negative 30 degrees. And the way that you take care of your horses in that kind of weather is either to house them or, and of course, most people don't have barns up there. Well, some of them do, but they don't usually put their animals in barns. What they will do is they'll leave them out grazing and they will feed them extra grain. The grain, of course, allows them to generate more heat. So during the wintertime, you usually feed what we did. We fed our horses oats, and we actually had a pole barn. Pole barns are three-sided barns, and the open side was pointed south. It was pointed south, and you rarely get wind from the south. And if you do get wind from the south, it's usually warm wind. So the horses were blocked from the wind because cold wind normally comes either from the north, the east, or the west. And they were able to generate their own heat because of the extra grain that we fed them. And we fed them a little extra hay too in the wintertime. At rest, the brain accounts for 1/3 of the heat generated by the body. As activity increases, the brain continues its level of heat production, but the muscles can increase their heat production tenfold. Humans can create heat by increasing metabolism, by breaking down brown adipose tissue, by shivering, and by increasing blood flow by constricting blood vessels. What else? I wanted to say something else about the horses. Oh, uh, horses evolve isn't the right word. Horses that live in warmer climates don't maintain extra fur for the wintertime. And we had an individual that he was a wolf tracker in New Mexico. And he wanted to bring his horses up to Montana. He was teaching chemistry for us at Fort Belknap College, now Ani Nakota College. And he brought his horses up from New Mexico, and because it doesn't get very cold in New Mexico, they weren't able to grow that extra layer of fur of hair to keep them warm in the wintertime. So what happened was he had had to put them in a barn for one thing, and he also had to cover them with a blanket so that they wouldn't get too cold. Anyway, and he complained about it a lot that it was so cold. He thought he was up in the mountains in New Mexico, but he didn't experience the cold temperatures that you experience in Montana. Anyway, there you go. So you can heat yourself if you're a human. You can heat yourself by increasing your metabolism, breaking down your brown adipose tissue by shivering, or by increasing blood flow by constricting blood vessels. Actually, horses do the same thing. Brown adipose tissue is found around vital organs in the thorax and around the cervical and thoracic levels of the spinal cord. Under cold conditions, the sympathetic nervous system stimulates metabolism within brown adipose tissue, which produces heat. Humans start shivering at 36.5 degrees centigrade or 97.7 degrees Fahrenheit. As I told you, my normal temperature is in the 96 range, so that's a little bit high for me. I usually don't start shivering. I don't shiver all the time, I can assure you. which starts in the face and it spreads down. But usually when you shiver, it starts in your face. Uh, uh, yeah. Well, anyway. When the human body is hotter than is safe for the individual well-being, brain cells can very quickly be adversely affected by the temperature. If the temperature isn't controlled, the body can cool itself through accelerated respiration, panting, and this is the way that dogs cool themselves, perspiration to cool the skin, and that's usually what happens. You sweat a lot. Dilation of blood vessels to release heat through the skin surface. Otherwise, in other words, your face turns red. So that's it. You perspire, you pant, and you turn red to stay cool. Some people sweat more than others. I was raised in Indiana, which it's not that cold in there. I didn't think it's not as nearly as cold as it is in Montana, but I sweat a lot more than most people do. I'm not exactly sure why. My wife hardly sweats at all. I'm not sure why that works out that way, but yeah, I sweat a lot. The human body doesn't seem to have just one thermostat, but it has three. The hypothalamus right here. There's your hypothalamus, this red chunk right there. The skin surface, your skin, and the body's core, primarily everything but arms and legs. And this is your core right here. This is one of the reasons why, if you ever watch any of those television shows where they have it's a detective story, and they have I can't think of the word, pathologist that comes and try to determine how long somebody's been dead. The first thing that they'll do is they'll stick a thermometer in the guy's liver. Now, why in the world would they stick it in his liver? Well, your liver's about right there. Nope, it's on the wrong side. It's right there. I'm assuming that this guy is looking the other way. Yeah, he's looking. I think he is. Anyway, he's looking the other way. So your liver is on your under your right rib. So it would be right there. Yeah, it's right under your right rib cage. It's kind of big, but yeah, you stick it in the liver. So the liver is right in the middle of your body. The reason it's in there, in the position that it's right there. The reason it's in the position that it's in is because it needs to be protected. So does your heart. That's why your heart's behind your rib cage. It's right under or just left of your sternum. Your sternum protects your heart, and there are vital organs that really need to be taken care of. One of them is the liver, another one is the heart. The lungs, of course, behind your rib cage as well. And your brain's got that skull around it. My goodness. Two other organs that are really important are your kidneys, one on each side. And strangely, your kidneys don't have anything really protecting them. They're kind of right there on the outside of your on the outside of your, well, it's not on the outside. It's right here. Here's your kidneys right here on the back. Anyway, as evolutionary biologists point out, humans have the same concentration of salt in our body fluid as the oceans of the world. It is therefore assumed that humans evolved from creatures in the sea who had to maintain a fluid and salt content similar to that of the sea. Thus, humans, as all animals, must not only monitor fluid levels, but salt levels as well. Osmosis is a special case of diffusion. In this case, a large molecule like starch is dissolved in water. The starch molecule is too large to pass through the pores in the cell membrane, so it cannot diffuse from one side of the membrane to the other. The water molecules can and do pass through the membrane. Hence, the membrane is said to be semi-permeable, since it allows some molecules to pass through, but not all cells can pass through. Semi-permeable. Except for deionized water, other forms of water that we might take into our bodies is in the form of a solution, a mixture of molecules of a solid molecules and water molecules. So it's got solids in it, mostly minerals and oxygen. It's got oxygen in it as well. So if you have ever tried to drink a glass of water that's been sitting there for 2 or 3 days, it tastes flat. It tastes funny. The reason it tastes funny is because it doesn't have any oxygen in it. Could have the minerals still in there, but it doesn't have any oxygen, and we're used to our water being running out of the tap and being in bottles and whatnot that hold the oxygen in. And you can smell it if you open a bottle of water. Try it sometime. Put the bottle of water right under your nose when you open it up, and you can smell the oxygen. It's really an interesting smell. A solution in this case is referred to as a solvent, and the solid dissolved in it is referred to as a solute. Semipermeable membranes will block the passage of the solute, but allow the water molecules to pass freely from one side to the other. The force or pressure to pull water across a semipermeable membrane is known as osmotic pressure. We refer to the concentration of a solute in a solution as the solution's osmolality. And this is one of the things that I did when I was in the service. We would get a urine specimen, and I had to measure the osmolality of the urine. Sodium chloride is a solute that the human body must balance in order to maintain a proper fluid balance. The human body must maintain a proper level of sodium chloride, salt, in order to function properly. Excuse me. That level of sodium chloride is 0.9%. 9 grams of sodium chloride dissolved in a liter of water. This is referred to as isotonic solution or as normal saline. Saline, of course, means salt water. Now, when I was working in the laboratory, if we mixed anything and we wanted to maintain its proper level, like blood, if you mix blood with water, then the red blood cells will rupture. If you mix it with anything else, if you mix it with isotonic solution, then it stays in its normal form. And that's the way we used to do our hematology, is by mixing it with normal saline. You can mix blood with normal saline and the cells stay exactly the same as they were inside your body. As interesting as all that is. A person who arrives in an ER severely dehydrated must be given fluids to replace fluid rapidly. But if they just give the person water through an IV, it would rapidly adjust the osmolality in their body. Therefore, the medical personnel would administer normal saline to the patient to replace fluids. In this case, the individual probably has more sodium chloride in their system than they need, and it is said to be hypertonic. Too much water and not enough sodium chloride would be hypotonic. Now, this can be a problem. So here you are, you're dehydrated, you need fluids. What do we put in? We put in normal saline, of course, because your body, at that point, if you are dehydrated, your body is hypertonic. Now, what if you drink too much water? That happens and people die from it. People will drink too much water before they run a marathon. It's called hypernatremia, and they will get too much water in their system. It will dilute out their blood. It will dilute out their body. They won't have enough salt in their system, and they'll go into shock and die. And that's because it's hypotonic. Their body is hypotonic. As weird as all that sounds. Okay, so I used to work with red blood cells. I used to do hematology. And when we were So we would mix the red blood cells with isotonic solution, and when we mix the red blood cells with the hypotonic solution, this is what the cells look like. Red blood cells look like donuts, kinda. They look like well, like donuts, about as good as anything. Yeah, that's what they look like. So if you put too much water in the if you mix the blood with water, this is what would happen. It would the red blood cells would the water would go into the red blood cells. They would expand, and this is what they would look like. Now, if there wasn't any salt in the water at all, and it was just pure water, then they would burst. The red blood cells would burst, or hemolyze is what we used to refer to it as. Now, if somebody's really, really dehydrated, then and their blood is hypertonic, this is what their red blood cells might potentially look like. Not all of them, because if all of them look like this, they would be dead. Your red blood cells have to look like this in order for them to for your red blood cells to carry oxygen, and of course you need oxygen to protect your brain. Your brain needs oxygen constantly. And if it's hypertonic, if you're dehydrated, this is what the red blood cells look like. This is known as a crenated red blood cell. Crenated. That's hypotonic. And if you're not careful, it will explode. So when we look at red blood cells, and what we will do, what we would do in the laboratory is, as soon as we drew somebody's blood, we would put a drop of blood on a glass slide, and we would make a slide. Now, at the end of the slide where all the blood was, the blood's too thick to even look at. So what we had to do, we had to smooth it out so that it made a rainbow at the end. And right there in the rainbow is where you could the cells were singular cells, so that you could look at each cell individually. Of course, if you made it incorrectly, you made your slide incorrectly, then you wouldn't have those single cells, and you couldn't really read it very well. So the best people made a really big rainbow, because the rainbow means that there's only one cell. So it's layered with only one cell. Down toward the other end, where it's nice and red, that means there's lots of red blood cells piled on top of each other. And of course, you can't read them because they're all stacked up. Okay, so now you know how the lab works. That's one of the reasons why. If you've ever had anybody doing a hematology on you, they probably made the red blood cell right away. And normally, what you like to do is make your slides as soon as you draw the blood, because then your blood is fresh. Potentially, if you didn't make any slides with the fresh blood, and you wait for 30 or 40 minutes, you can make it out. You can make a slide out of the tube, but of course it's been sitting in there for 30 minutes, and there's always a possibility that something has happened, and it's not as accurate as it would be if you made it right away. How weird is that, huh? Why am I talking about this? Internal cues that trigger thirst. Hypovolemic thirst is thirst that's caused by low volumes of fluid. You have baroreceptors in the major blood vessels detecting any pressure drop from fluid loss, usually caused by rapid loss of body fluids, such as hemorrhaging, diarrhea, or vomiting. Then your baroreceptors will kick in, and it'll tell you that you need to drink something. Osmotic thirst, high volumes of solute in the extracellular fluid. Osmoreceptors in the brain detect any increased osmolality of extracellular fluid. In other words, you've got too much salt. Hypovolemic thirst, when the baroreceptors detect a drop in blood pressure from tension in the artery walls. The information is relayed to the autonomic nervous system. The blood vessels constrict to maintain proper pressure for consciousness, otherwise you'll pass out. That's when people get dizzy if their blood pressure drops too low. The brain also releases vasopressin, antidiuretic hormone, from the posterior pituitary gland. Vasopressin acts on the kidneys to reduce flow of water to the bladder. So what does that do? That increases the amount of water in your system. That's what vasopressin does. Hypovolemic thirst in diabetes insipidus, vasopressin is not produced and the kidneys will not retain water. The patient is constantly thirsty, drinks lots of water, and urinates constantly. The urine tends to be almost completely clear. And you should look at your urine. You should look at your urine. You really should. You should look at your urine and your stool specimen or your stool to determine if you've got anything wrong. You're not being sick. You're not being strange. You're being cautious. And it's a really good idea to look at your urine to see how dark it is, to see how clear it is. The clearer it is, the better off you are. It means there's no bacteria in there. It means you don't have anything else that could potentially be bothering it. If it's a strange color, that may mean that there's a problem with your kidneys. You have a kidney infection. If you've ever had a kidney infection or you've ever had a urinary tract infection, you know what it feels like. And probably if you collected a urine specimen, it would be fairly cloudy, and that's not good. That's not good. That's not good. You need to get that taken care of because the bacteria that infect your kidneys or infect your bladder can potentially infect your kidneys, can cause a lot of damage. And so you need to get that taken care of as soon as possible. The kidneys also detect low blood volume and release a hormone called renin. Renin triggers a protein called angiotensinogen to form the protein angiotensin 1, which in turn becomes angiotensin 2. Okay, so look at your stool. What are you looking for if you're looking at your stool? It needs to be brown. Brown's good. Could be green. That's okay. That means you've been eating a lot of vegetables. If it's white, it means you've got blood in your stool. If it's black, it means you've got blood in your stool. White means that you're bleeding in your colon, I think. And black means you're bleeding into your small intestine. Anyway, if you've got black tarry stools, you need to go see the doctor. If you've got white stools, you need to go see the doctor. Okay, and that's the reason why you need to look at your stool. We had this guy came into the emergency room one time. He was on Coumadin. Coumadin is a blood thinner, and he was on Coumadin. And he was an older fella, World War II vet, came in, and by golly, when we drew his blood, he was so anemic, he was almost dead. He really was. He was in really bad shape. So what happened was, he collected us a stool specimen, and it was white. So what was going on? He was bleeding out. He was bleeding in his intestines, and of course it was showing up as a white stool. But he never looked at his stool, so he didn't know that. He didn't know that anything was wrong, and he almost bled to death. So look at your stool just to make sure there's no blood in there, just to make sure it's the right color. The right color is any color of brown or any color of green is okay. Black and white's not good. That means blood. Hypovolemic thirst, angiotensin 2 constricts blood vessels. It triggers the release of vasopressin. It triggers the release of aldosterone, which is a sex hormone, an androgen. It acts on the preoptic area of the brain to elicit the feelings of thirst. This is accomplished in the subfornical organ, one of the circumventricular organs around the open areas of the ventricles of the brain where the blood-brain barrier are weak. Osmotic thirst is more common than hypovolemic thirst, and as the name suggests, it has to do with an imbalance of sodium chloride in the extracellular fluid due to a loss of water. Osmotic thirst is caused from perspiration, respiration, and urination. If you perspire too much, you're going to have a high salt level in your body. If you breathe too hard, you'll have you breathe out fluid, and of course that will increase your sodium chloride. And if you urinate too much, that gets rid of fluid as well. The other thing is diarrhea, of course. You can, if you have diarrhea, you're losing fluid instead of solid mass, and you can dehydrate very rapidly. Since we are dealing with an increase of sodium chloride in the system, this form of thirst can be triggered by eating salty foods. Osmotic thirst, research shows that humans have has osmoreceptors in the various areas in the preoptic area: anterior hypothalamus, supraoptic nucleus, organum vasculosum of the lamina terminalis. Sodium chloride balance in the body is very delicate. As we have noted before, hypertonicity or hypotonicity will cause cell destruction. When angiotensin II is released in the bloodstream, it acts on the adrenal glands to release the mineral corticoid steroid hormone aldosterone. Aldosterone acts on the kidneys to conserve sodium, which in turn allows the individual to conserve water in the body. More sodium equals more H2O. The more sodium you have in your body, the more H2O you will maintain. However, humans cannot drink seawater. It is hypertonic and thus adds more salt than water, causing greater thirst. While humans have not evolved to handle hypertonic conditions, creatures that live in the ocean or are able to survive with little water have kidneys that can handle large volumes of sodium chloride. Not only do organisms require water and warmth to survive, but they need food as an energy source. If this were the extent of our needs, humans could eat raw glucose and live very well. However, humans also require nutrients, chemicals that do not provide energy but are required for the proper functioning of the body. Some of the nutrients that we require are in the form of amino acids. Of the 20 amino acids required by the body, 11 are manufactured internally, and 9 must be attained through our diets. These 9 are called the essential amino acids. Besides the essential amino acids, our bodies require 15 vitamins, several minerals, and a few fatty acids from our food. These nutrients are obtained when the body breaks down complex foods into simpler forms through the process of digestion. Most animals, especially humans, will build up stores of nutrients in their body. This is done because our anthropologic ancestors tended to go through cycles of feast and famine. And the individual who could not establish stores of excess nutrients, usually in the form of fat, would not survive to reproduce. All the energy we need to move, think, breathe, and maintain body temperature is derived in the same way. It is released as the chemical bonds of complex molecules are broken to form smaller, simpler compounds. To raise body temperature, we release the bond energy as heat. The amount of energy used is expressed in kilocalories. While not all foodstuffs provide energy, which cannot be used is excreted, especially as solid waste. Available energy is used in one of 3 activities: processing of newly ingested food, about 33% of energy utilization; basal metabolism, maintaining the body, about 55% of energy utilization; and active behavioral processes, about 12%. So if we exercise, we're only dealing with about 12% of the total calories that our body will burn. When you're asleep, you burn this much because that's when your basal metabolism kicks in and you are maintaining your body. That's why sleep is so important. You're utilizing 55% of your energy stores. And of course, digesting food takes about 33%. The body uses glucose as an energy source and so breaks everything eaten into this form. Glucose is stored in the body in the liver as a substance called glycogen. When ingested, glucose is low, the body will release glycogen from the liver to keep the brain functioning. The release and breakdown of glycogen from the liver is controlled by two enzymes from the pancreas. Glucagon promotes the breakdown of glycogen to glucose in a process known as glycogenolysis. Insulin promotes the conversion of glucose to glycogen. So it's glucagon and insulin are the two enzymes from the pancreas. When an individual has been without food for a prolonged period, either forced or due to dieting, they begin converting their adipose tissue into glucose in a process known as glucogenesis. At the same time, they will produce a secondary fuel called ketones, which can be used by the body and the brain as fuel. And ketones stink. I'm sorry, they do. Long-term energy stores are in the form of fat cells or adipose tissue. Adipose tissue can be used for energy when the ready amount of glucose in the system has been depleted. Adipose tissue can be broken down into simpler forms, fatty acids, and glucose. Glucose is brought into individual cells through glucose transporters in the cell membrane. Glucose transporters can only function when they interact with insulin, except for brain cells, which do not need insulin to function. Otherwise, diabetes mellitus would cause such severe brain damage that it would be instantly deadly. There are three phases that the body must go through to be able to utilize glucose in the diet: the cephalic phase, the digestive phase, and the absorptive phase. This is really important. Glucose is the only energy source that actually it breaks everything down into glucose. Our body breaks everything down into glucose. Now, the strange thing is that the brain cells are able to utilize glucose without insulin. Thank goodness. Yeah, well, we saw what would happen if they needed insulin to work, to function. The food itself acts as a stimuli: sight, smell, and taste. This evokes a conditioned release of insulin in anticipation of glucose arrival in the blood. In this phase, the release of insulin is regulated by the brain and is thus referred to as the cephalic phase. In the digestive phase, food entering the stomach and intestines causes a release of gut hormones. This stimulates the pancreas to release more insulin. During the absorptive phase, glucose enters the bloodstream and special cells in the liver, the glucodetectors or glucostats, detect circulating glucose and signal the pancreas to release more insulin. Insulin allows the body to either utilize the glucose immediately or convert it into glycogen. The nerve that passes information from the liver to the brain and back to the pancreas is the vagus nerve. The vagus nerve runs to the nucleus of the solitary tract in the brainstem. Diabetes mellitus, lack of insulin, causes a disease called diabetes mellitus. Type 1 juvenile onset diabetes mellitus, the pancreas stops producing insulin. Though the brain can still utilize the glucose from the diet, the rest of the body can't, and so it utilizes fat stores instead. Since most of the dietary glucose cannot be used, it passes through the system and is excreted in the urine. And we can detect it with the dipstick that tells us how much glucose is in your urine. Glucose can also not be converted to glycogen and stored in the liver. Diabetics are hungry because the body tells them to consume energy, but they can't gain weight because they do not store glucose as fat. treatment is to provide exogenous insulin. And that's type 1 diabetes. Juvenile onset, you're usually born with it. Diabetes mellitus type 2, adult onset diabetes, what we used to call adult onset diabetes, but by golly, we're seeing more kids that are coming down with type 2 diabetes. It's just amazing. When I first started working in medicine back in the 70s, you never saw a kid with type 2 diabetes ever. You never, ever, ever. But now there are percentages of kids that have type 2 diabetes. It's just amazing. Um, we used to talk about type 1 and type 2 diabetes. You develop type 2 diabetes when you were an adult, when you got a little bit too paunchy, started putting fat on around your gut, and that potentially could cause type 2 diabetes. Type 1 diabetes we used to call it juvenile onset, but geez, now there are so many kids with type 2 diabetes. We're thinking it's probably diet. So when I say adult onset diabetes, I'm really talking about the old days when diabetes mellitus type 2 was only adult onset diabetes. It's usually a milder form of diabetes, but that usually does not affect an individual until they're adults. But well, we're seeing it in juveniles now. There are two causes of this type of diabetes. The cells gradually lose their sensitivity to insulin. The body gradually decreases its production of glucose. This type of diabetes is more common among obese people and can usually be controlled by reducing the amount of glucose in the diet. The individual can also take medications that stimulate the pancreas to produce more insulin. And we used to use metformin. I'm not sure what is being used now. I think metformin is still being used for type 2 diabetes. Many people prefer the foods that they grew up with. People are drawn to sweet foods and fatty foods because their taste is satisfying. People also are drawn to salty foods because we need the sodium chloride to maintain homeostasis. Now, this is all natural. It's natural for us to crave sweets. It's natural for us to crave fatty foods. It's natural for us to crave salty foods. So liking sweet foods and liking salty foods and liking fatty foods is evolutionary. Makes sense. People who are hyperhydrated might actually crave salt. In other words, if you've drunk too much water, then potentially you will crave salt. People develop taste aversions to foods that poison them and make them ill, and these are known as taste aversions. Most toxins are bitter tasting. Some people suffer from neophobia, the fear of new foods. My grandson seems to fear new foods. He doesn't want to go to this restaurant because he hates the food there. He's never been to that restaurant before, but he hates the food. He's a little snot. We'll cure him of it eventually. One of the hormones released in the stomach and intestines is cholecystokinin, also known as CCK, which comes from the gallbladder. And I like the word cholecystokinin, so I'm gonna use it. Cholecystokinin is released if foods have a high content of fat and or proteins. Cholecystokinin also stimulates the pancreas to release insulin. Cholecystokinin may be one of the satiety signals. However, to inject cholecystokinin into someone as a means of controlling hunger causes nausea and cramping, so you can't do it. Cholecystokinin in the presence of food activates the muscles of the intestines to work. Absence of food leads to feelings of nausea and cramping. So there you go. You need it. This comes from your gallbladder, of course. Yeah, I've already said that. Hunger triggers, how insulin in the blood is an obvious trigger to eat. I'm sorry. Low insulin in the blood is an obvious trigger to eat. However, high insulin levels do not equate to satiation. Satiety appears to be spread over various regions in the brain, including the amygdaloid nuclei, the frontal cortex, and the substantia nigra. Leptin is a protein produced by fat cells that is secreted and informs the brain that the individual has had enough food. Obese people seem to be insensitive to leptin's message, and that is why they eat to excess. When leptin reaches the hypothalamic arcuate nucleus, it suppresses the release of several peptide neurotransmitters that induce eating. And two of these are neuropeptide Y and a agouti-related peptide. Leptin also enhances the release of peptide alpha melanocyte stimulating hormone. Now, agouti is kind of interesting because we discovered this by looking at that animal. That's the agouti. It's a South American rodent. It's big. It's really big. I've been to South America and I have seen the agouti. They're pretty big. Anyway, they're kind of ugly. Anorexia nervosa and bulimia nervosa are two disorders. Are two disorders of hunger management that leads to extreme emaciation and even death. Anorexics commonly desire and think about food, but deny themselves sustenance. The basic problem seems to be a distorted body image where the individual sees themselves incorrectly as overweight when they are actually thin to the point of death. Anorexics tend to be slender to build or begin with, and slender of build to begin with. I'm reading too far ahead. And the excessive dieting merely adds to emaciation, and that's what an anorexic looks like. They are way too skinny. I'm sorry, they're way too slender. What did I read? Within 10 years, 10 to 20% of anorexics die. Within 20 years, it's 30 to 40% of them will be dead. Why? Because they relapse. This gets stuck in their heads and they can't eat. Bulimics tend to be a little plumper than anorexics. Bulimics are able to control their weight by purging the food from their system, either through exercise, vomiting, or laxatives. Bulimics will also go a little crazy from time to time and eat massive amounts of food at one sitting, and then relieve themselves of it through vomiting. This is known as binging and purging. And that is the end of the chapter. So I'll talk to you again next week. I can't remember what we're tackling next week, but I'm sure it's something equally as fun as homeostasis.